In this video, we explored the chain rule. So this is a rule for taking derivatives really of what we would call composite functions or compositions of functions. Very seldom do we just have an x squared or a cosine x just by itself that we take a derivative of. It of course happens, but we need those rules to then take derivatives of more complicated things. For example, here I want to start off with something like y equals square root of x squared plus 1, right? So this is what I would call a composition function. I can break this apart into a couple pieces. This is like y equals the square root of u, right? And I'm just taking u out, basically thinking about the square root function by itself. And then what's underneath, x squared plus 1. So x squared plus 1, I can think about it as kind of its own function. It's inside the square root function. Okay? This is called a composition of functions, right? I've got one thing inside another. And the chain rule is meant to deal with situations like that when we're taking derivatives. Right? So when we do this, I'll try to kind of, to not derive it, but at least kind of take you through how it comes about and kind of get the logic out of the way through a couple examples, and then we'll do some other ones just going through and using the formula that is chain rule. Okay? So first thing I want you to know is that chain rule is everywhere. You're always using chain rule. Okay? You learn it and think about it like it's its own special thing, and I only use it in certain situations, right? But I really try to think about it always. Do I have a chain rule step here, yes or no? No? Okay, I'm good, I'm done, my derivative's over. Do I have a chain rule step? Yes, I do. Let's do it. So what we have is this function, square root of x squared plus 1, and I want the derivative. I want dy dx, okay? None of the rules we know so far apply directly to this function, right? I can't just do a product rule here. I don't have a product. There's no quotient. So I tried to work my way around this. And basically we take it kind of piece by piece. We have what we would call the outside function, the square root function. I can take a derivative of that, dy, with respect to u, right? Dy dx is the whole thing. That's my derivative. Dy du is kind of the derivative of the outside function, right? Because u is u there is being raised to the 1/2 power. When I take a derivative, I end up with 1/2 u to the minus 1/2, or 1/2 square root of u. So that's a derivative of y as if u was my variable, okay? I like to think of this as like the derivative of the outside function, okay? I also have to remember that u is a function of x. U is a function of x. So when I take a derivative of y with respect to x, I also have to consider what's inside. What's the inside function? What is u? And I also need the derivative of it. Derivative of u with respect to x is just 2x, right? Derivative of x squared plus 1 is a 2x. The chain rule is kind of both of these things together, dy du and du dx. So what we have is the derivative of y with respect to u times the derivative of u with respect to x. This is what we call the chain rule. And I actually really do like to think about it as kind of like chain links that are together, right? To get this kind of overall derivative, I need to take the derivative of the outside function and multiply it by the derivative of the inside function, okay? Now, we won't always just have these kind of 2 layers. There might be 3 layers or 4 layers where we have a kind of a bunch of chain rule links all stacked together, okay? So what I'm going to try to do, I'll finish this example here, and then I want to do this kind of a different way as well. So then my derivative, I can write dy du is 1/2 square root of x, right? That's right there. Times du dx is 2x. But my derivative, y, is with respect to x here, so any u should be taken and replaced with what what u actually is. I see that these 2's cancel. I'm left with an x in the numerator, and u is x squared plus 1. And I've got my derivative. So that there is what we would call the chain rule. I had to use the chain rule because I had an inside function whose derivative also needs to be considered. Let's do another example. I've got y equals tangent of e to the x, and I want the derivative of this guy. Okay, I'm going to kind of break this apart using similar notation, but also a little different. I've got here kind of an outside function. I'm going to say that f of x is tangent of x. This is the outside. And then g of x is going to be my inside, which is at e to the x. This means that I can express y as kind of like f of g of x, right? I've got a composition. Tangent has e to the x inside it, tangent of e to the x. I've got f of g of x. So when I take a derivative here, I'm going to work my way kind of outside in to take this derivative. What I've got then is like f, and trying to incorporate some of the previous notation, y is going to be like f of u or tangent of u. Okay, that should be y, not quite y prime yet. So I'm just rewriting my function there. And to take a derivative, I have to remember what u is. Okay, I have to remember that u is g of x or e to the x. So when I go to take my derivative there, I've got chain rule. dy dx is dy du times du dx. Okay, that formula is a little weird and it's maybe a little bit difficult to remember, but through some other examples we do, I think you'll get a hang of what the chain rule actually is. So this can be rewritten, my chain rule can be rewritten as df du, right? Y is like f, df du, times du dx, okay? Where df du, derivative of tangent of u, is secant squared of u, okay? Times the derivative of u with respect to x. I'll leave that there for now. I want to try to incorporate g. So I've got df du, and du dx, there's u. I need to take a derivative of that with respect to x. That's the same as taking the derivative of g with respect to x. So really, I can write this also as df du times dg dx, derivative of g with respect to x, is e to the x. And then all I have left to do, du dx is dg dx is e to the x. All I have left to do is rewrite what u is, and that's just my e to the x. If we zoom out a little bit, derivative of tangent of e to the x is secant squared of e to the x times the derivative of e to the x. Okay, I've got to multiply by the derivative of the inside function, and that's where this second e to the x comes from. Okay, so what we're able to do is kind of generalize this. Okay, so what I like to write here is that if y equals f of u and u equals g of x, this composition, f of g of x, has a derivative that's dy dx is dy du times du dx, or with f's and g's, we write this as derivative of f of g of x is f of g of x with the derivative f prime of g of x times the derivative of the inside g prime of x. So there's both with the what we call Leibniz notation, with the dy du and du dx, and also with the prime notation, f prime of g of x times g prime of x. A lot of people tend to like that second notation more. It helps them kind of get a better idea of what's going on. Let's do some more examples. I think things will become more clear as we go. So here's my function I want to take a derivative of, 3x plus 2, all raised to the 5th power. So without the chain rule, we would have to take this binomial, 3x plus 2, and raise it to the 5th power. Actually multiply it out 5 times, FOIL 5 times, collect like terms. We'd end up with a polynomial of 5th degree that we would take the derivative of. It wouldn't be too hard, but getting there is a real pain. So thankfully, we have this chain rule to help us out. And the way we work through it is I kind of work my way outside in. I would say the outside function is like the 5th power, right? I'm taking something and I'm raising it to the 5th, u to the 5th. The inside function, g, I would call 3x plus 2. I know I need the derivative of both of those, right? So my chain rule goes like this. The derivative is going to be dy du, derivative of y, f with respect to u. And that's going to be 5u to the 4th. Okay? times the derivative of u with respect to x. U is 3x plus 2, so the derivative of that is just going to be a 3. And all I have left to do is plug in what u is. So I've got a 5 times 3x plus 2, that's u, all to the 4th power, times a 3. I can just quickly simplify this to 15 times 3x plus 2 to the 4th power. So I work my way outside in. I think about the outside function being like that quantity to the 5th. How would I take a derivative of something to the 5th? Well, that's 5 times the something to the 4th power now. I subtract 1, bring the power down. I'm using my power rule. And then I take the derivative of the inside and multiply them. Okay? Let's do another. I've got the cubed root of x squared minus 1 all squared. Okay, so I've got a radical function this time. The derivative really isn't too much different. I do, however, want to rewrite this a little bit. Being raised to the 2/3 power is the same as taking the third root and squaring. Okay, so it's much easier if I write that all as one exponent all to the 2/3. Okay, so my derivative here would be outside in. I've got this outside function and inside function. Derivative is I bring the 2/3 down, leave the inside the same, and I subtract 1 from the power. Okay, the inside remains the same. F of g of x, right? The derivative is f prime of g of x, not f prime of g prime, right? It's f prime of g. So the inside stays the same. Then I multiply by the derivative of the inside function. Okay, inside stays the same. Multiply by the derivative of that x squared minus 1, and I get a 2x. I can simplify a little bit. 4/3 x times x squared minus 1 to the minus 1/3. And then I can make that with a positive exponent and write my quotient then. Okay? Derivatives, not so bad. Not so bad. It's just we have to pay attention to what the layers we're working with are and how the chain rule is going to come about with the specific example that we have. Work my way outside in. We can generalize this. Also, the nice thing here is, I should say, a lot of the times we're focused on when the derivative would be 0 or the slope of the tangent line, plugging in a point. But it's nice here, we can easily take that derivative and set it equal to 0. Okay? So as some of these examples come, think about what would happen if I would take that derivative and then set it equal to 0. How would you solve that? What would you do? I'm not going to work through that here. I just wanted to make a little note. So we can generalize this kind of pattern here. This chain rule, yes, it's all chain rule, but what we have from this is called the generalized power rule. If we've got a function, u of x, all raised to the power n. Okay, so I'm kind of mixing some notations here. If I've got u to the power n, that derivative would be n times u to the power n minus 1. But then I have to make sure to multiply also by the derivative of u. Okay, so there's my power rule generalized, right? So instead of just x to the power n, I can now take the derivative of u to the power n. It's stronger. Let's do another. Here I'm changing variables on you. I've got a function of t minus 7 divided by, parentheses, 2t minus 3, then to the 2nd power. Okay? So a derivative of this, not so bad. It's a quotient, but you notice very quickly you do not have to use quotient rule if I write the denominator with a negative power. Okay, so quotient rule is not required here. I just write negative 7 times 2t minus 3 all to the negative 2nd power. When I take this derivative, again, I work my way outside in. I don't take the derivative of that negative 7. It's tempting, but negative 7 there is just a constant multiple. So when I go to take my derivative, I leave that negative 7 out there. I take the derivative of something to the negative 2, right? I bring the negative 2 down. Inside is going to stay the same, 2t minus 3. Subtract 1 from the power, and I get negative 3. Then I also have to multiply by the derivative of the inside. I could have gone right to that, but I decided to write it with some notation there. So you see where this piece is going to come from. Derivative of 2t minus 3 is just going to be a 2. So that's right there is my chain rule step. So when I write that multiplication there, that's when that chain rule is applied. Anytime I've got an inside function. Okay. So just simplify a little bit here. This is going to be equal to, I've got negative 7 times negative 2 times 2, and that can all be simplified to a 28, times 2t minus 3 to the negative 3, or written with a positive exponent, 28 over 2t minus 3 to the third power. Okay? Good. So, chain rule is becoming a little bit more clear as we go through these. I've got a couple more examples I want to do with you. Let's look at e to the minus x. E to the minus x, when I take a derivative, work my way outside in. I've got the derivative of e to the something is e to the something. So I've got an e to the minus x, that exponent's going to stay the same, times the derivative of the exponent, times times the derivative of minus x is a negative 1. So that's minus e to the minus x. Okay. Take these a little slow. I'm going to go through a couple more and kind of talk through each one. Second example, secant of 4x. Okay. Outside in, I take the derivative of secant of something. Y prime here would then be secant tangent. Derivative of secant is secant tangent. So these 4x's have to come along for the ride, but I also then need to multiply by the derivative of the inside. The derivative of 4x is a 4. Okay? There's not a lot I can do to simplify this. So let's go on to the next one. I've got sine squared of x. Doesn't seem like I would need chain rule here, but this is really sine of x quantity squared. So what I've got is a function, it's composition, right? I've got something squared, right? I'm taking the derivative, the outside function is the square, so when I take a derivative, I bring the 2 down, leave the inside the same, and subtract 1 from the power. So I've got 2 times sine of x all to the first power, times the derivative of the inside, derivative of sine of x is a cosine of x. So all of this I can write as 2 sine x cosine x. Okay? The fourth example here, notice the difference. Sine of x squared. Not sine squared of x, but sine of x squared. This is different. I've got actually here sine of x squared. The x is being squared, whereas before I've got the whole sine function being squared. Okay? This guy, when I take a derivative, working outside in, derivative of sine of something is cosine of something. The inside stays the same. I then need to multiply by the derivative of the something is the 2x. So what I've got here is 2x cosine of x squared. Okay? And you can incorporate the parentheses around that x squared if you want. That's kind of up to you. I didn't have them to begin with, but just know that if things are written this way, that it's not all of my sine function squared, but my x is being squared here. So what I should say is just be careful with parentheses, right? We've got functions inside of functions all the time. It's just my parentheses are going to help me identify which is the inside, right? What do I actually have here? And help me kind of be able to visualize my order of operations. Let's go through another example, number 5. I've got cosine of negative 2t, but that's cosine cubed of minus 2t. The first thing I want you to notice is that I don't have a product here. We very frequently think about this as a product rule. It is not. I've got cosine of minus 2t, that whole thing cubed. Okay, so this is not a product rule. It's just a big, long chain rule problem. In fact, I've got layers. In fact, there's 3 of them there. I've got an outermost function there is the third power. I've got something to the third power. The inside of that is cosine of something. Cosine is my second layer. Then minus 2t is finally kind of the third layer, and that's pretty much it. So when I take a derivative of all this, I'm going to work layer by layer. I'm going to go outside in. So y prime then, derivative of something cubed is 3 times the something squared. I'm going to multiply this by the derivative of the inside, derivative of cosine of minus 2t. Okay? That derivative has its own chain rule. Okay? So this multiplication here is my chain rule step. But when I go through and then take the derivative of cosine of minus 2t, there's chain rule that I have to pay attention to there as well. Okay? Derivative of cosine, there I just keep rewriting the second bit. Derivative of cosine is minus sine. Inside stays the same again. So I've got now derivative of derivative of cosine of minus 2t is minus sine of minus 2t times the derivative of minus 2t is just a minus 2. So I'm going to buzz right to that. Derivative of minus 2t is minus 2. So we can collect things a little bit here and make them a little nicer. I don't really have 3 derivatives here. It feels like it. I just have layers. So the derivative, y prime, the first derivative of this big composition of functions, this multi-layered function, is just 6 sine of minus 2t times cosine squared of minus 2t. So I can multiply. I've got 2 negatives, make a positive, and 2 times 3 is a 6, and I'm done. Okay? And again, that square, the exponent, this square, doesn't mean that I'm squaring cosine and negative 2t, right? I'm squaring the cosine function that's taking cosine of minus 2t. Okay, I hope that makes some sense. So anytime we've got layers, we're always working our way outside in. Watch for multiple layers. You'll have a chain rule step for each layer. Just be careful. There's a couple of those in the section, and you'll see them more and more as we go on. I want to do one final example with you guys. Say we want to find the solutions to f prime of x equals 0, where f of x is x squared times square root of 1 minus x squared. So this is similar to the problem that I kind of started the section with, but I'm applying it. All right, I want to specifically look for when this derivative is equal to 0. And actually what that means is I'm finding horizontal tangent lines. Okay, so to do that, I want to take a derivative. And I know then that I have a product rule because my function is a product, right? So my derivative should look like x squared times the derivative of the square root function there, derivative of 1 minus x squared to the 1/2, plus the square root function times the derivative of x squared. Okay, so I'm going to go through this a little bit. I keep my x squared the same. Derivative of 1 minus x squared to the 1/2, I've got chain rule here. I've got a 1/2 that comes down, keep the inside the same, and subtract 1 from the power. So I've got 1/2, 1 minus x squared to the minus 1/2, times the derivative of the inside is a minus 2x. Okay, derivative of 1 minus x squared is a minus 2x. Chain rule. Plus square root of 1 minus x squared, derivative of x squared is a 2x. No real chain rule step there, right? We kind of do it, but it's the derivative of like x. X is our inside function, and the derivative of x with respect to x is 1. So there's really, the chain rule stops there. But there in pink, you see I've actually got a chain rule step. I've got an inside function to the square root, and that's why I see that extra minus 2x come into play. I'm going to simplify a bit here. I see that a 2 and a 1/2 are going to cancel, and I'm left with x squared times an x in pink is an x cubed, and there's a minus there as well. 1 minus x squared to the minus 1/2 is often written then in the denominator as the square root of 1 minus x squared. There's really nothing to simplify on the other side of that plus sign. I've got just a 2x times my radical 1 minus x squared. Okay? I eventually want all of this guy equal to 0. I want to set this equal to 0 and solve for x. And I want the easiest way that I can do that possible, right? I want the easiest amount of work. So what you could do is subtract one term to the other side, kind of cross multiply. That would work, okay? We just have to be a little bit careful when we do that. What I'm going to do here is actually get a common denominator, okay? And in doing that, what's going to happen is I'm going to end up with a single fraction that I can set equal to 0. My common denominator here is just going to be the radical. In the numerator, all I'm going to have is minus x cubed plus 2x, because my common denominator I get by multiplying square root that second term by square root of 1 minus x squared. And when I do that, the numerator, the radical, is going to cancel, and I'm left with just this 1 minus x squared. Okay? Radical 1 minus x squared times itself, the radicals disappear. Denominator becomes square root of 1 minus x squared. But that's the same denominator as I have here, right? I've got a common denominator now, so I just have one entire denominator, square root of 1 minus x squared. I simplify as much as I can, okay? Not a lot I can do. I'm going to distribute this 2x in and end up with a negative 3x cubed plus a 2x and leave my denominator the same. And then you'll notice here I've got an x in common, and I'm going to factor that out. In fact, I'm going to pull out a negative as well. So I've got some freedom there. But again, the goal is to set this all equal to 0. And to do that, I've got a fraction equal to 0. Fraction is always 0 when the numerator is 0, right? Think like 0 over 10 is 0. Fraction is 0 when the numerator is 0. So I set minus x, 3x squared minus 2 equal to 0. And I've got a product then equal to 0. My calculus is done. All of this now is just algebra. So when I've got a product equal to 0, either the first term is 0 or the second term is 0. So this means x equals 0, or 3x squared minus 2 is 0. And when I solve that, it gives me that x should be plus or minus the square root of 2/3. Okay? Done. That's it. But I've got 3x values then when my derivative is 0. So again, what I've got here is horizontal tangent lines, or the locations, the x values, for when my function has horizontal tangent lines. This is something that we're going to be really interested in as we continue on through the semester. When does a function have horizontal tangents, and what can that tell me about the function itself? Okay, so again, chain rule is this kind of process that we have existing kind of all over the place, where we're always looking for where it applies. When do we have an outside function and an inside function? Where do I have to always pay attention to the derivative of the inside? That's chain rule. Okay, you should do a lot of practice here. Okay, so try to remember the rules from before. Those are all going to exist and keep coming up. We've got power rule everywhere. We've got constant multiple rule, sum and difference all over the place. Product and quotient rules too. The derivatives of our trig functions are very important. And also now chain rule we have everywhere. Okay, that's all for this video. Thanks for watching.